And we are live, at least it is listed here, so I hope it is not lying to us. So hello everyone in the second talk today, which will be about parallelism, which is a lot of fun, I agree. So we will follow with Oleg. Hi Oleg, nice to meet you. Unfortunately online, but let's see, maybe next year. As far as I remember, we have met in Minsk at the conference, one of the conferences, or maybe at another conference. There are so many of them. So maybe we will meet also next year, for example, maybe it will be better. So you are a .NET developer, you will introduce yourself, and we are super keen to watch your talk. So I'm just hiding myself, and the scene is yours. Let's just listen about parallelism in .NET.
Thank you, Konrad, for the introduction. So, making fun with parallelism. My name is Oleg Karasik, and that's actually me, actually a younger version of me. And I am a technology lead in Iis. It's a company in Minsk, Belarus, and I code in .NET for more than 10 years. So during these years, I participated in development of different kinds of application. Web application, desktop application, frameworks, shared libraries, and utilities. So I was lucky to touch .NET from very different perspectives. However, besides work, I also tried to do something, and particularly I try to contribute into open source. I occasionally publish blog posts in my blog, and I do in my newsletter, which is called .NET R&D Digest, and maybe some of you even heard about it. And of course, I do some parallelism. That's true. I like things that can be parallelized. So what this presentation is about? So what will we be talking? So I bet many of you during your career hear something like, we can use task parallelism here. Or this algorithm makes use of divide and conquer strategy. Or, which is, by the way, will be very, very surprising, you might hear something like, this is called synchronous parallelism. But, this sounds really cool, but what these things really are? So what is task parallelism exactly? So what does it mean? And how there could be such a thing like synchronous parallelism? Does it sound like it contrary things? So during my talk, I will try to explain and demonstrate all of these things and map some of them to the .NET code. And in the end, if we will have time, I hope, I will demonstrate you a very interesting way to use some of this theory in practice. So let's go. And let's start from the basic concepts, because you cannot, lay anything without a foundation. So I have selected 6 basic concepts we will quickly cover to better understand all the things I will talk later. So the first one is a thread. So there are many, many definitions of threads, and actually most of them are precise and technically correct. However, for current presentation, I will use some abstraction, and I will say that I will call thread a path of execution within application, which is carried out by a dedicated stateful actor. Let's do not concentrate on what this stateful actor is and how exactly it carries out the execution. I will come back to this in the end of the presentation. For now, let's just assume it's that way. So our path of execution consists from operations. So actually, thread execute operations, and operation can be as small as subtracting 2 numbers, or it can be really huge, like, for example, calculating a shortest path in a graph. And the next 5 concepts I selected, they form, I think, as I call it, a circle of confusion. So while thread is quite clear, we see threads all the time. These 5 really looks, connected, like they tighten it up, like any of them are so close that it's sometimes really hard to distinguish between them. But the really fun fact is that they are not related to each other. And they do not relate to each other because they are simply focused on different things. So they are just about different things, which, by the way, interact with each other. But the concepts are clearly not. And to better understand this, let's start from defining what is synchronous and asynchronous execution is. Let's see a small example. So imagine we have a thread which starts the operation and then this operation completes. So our thread does nothing until the operation is completed. And the operation itself can be either carried out by our thread, so thread can start, execute operation, and then it will reach the operation end, or our thread can wait for the operation to be carried out by someone else, for example, by another thread. So in this situation, we can say that thread's execution is bound to operation completion. So if operation never completes, thread never proceeds. So they are bound to each other. However, if we look at different examples of how thread can execute operations, we can see that actually thread can start the operation and continue without waiting for operation to complete, like fire and forget. Or we can extend the first example and say, okay, our thread started the operation, did something, some other operations, for example. Then it started to wait for this operation to complete. However, even in second case, thread's execution isn't bound to operation completion. So thread actually can continue do its work, and this can be really a lot of work. And while on the graph, the operation beautifully ends after the thread done with its work, it can be otherwise seen. So what these examples demonstrate us is that actually this is the way to define what we call synchronous and asynchronous execution actually. So when thread execution is bound to operation completion, it is a synchronous execution. And when it is not bound, it is asynchronous. And it is because both of these things are really focused on what thread does when it starts the operation. So this is the really important fact for us. If we start the operation and do nothing, synchronous. If we do something and then wait or do not wait, asynchronous one. So we can simplify it even more and say that synchronous and asynchronous execution focus on what caller does, actually. Now, let's try to think about parallelism. So this is a really, really best example of parallelism you ever can see. And when we have two threads that starts execution of their operation and do it all the way long. So everything between these threads happening at the same time. So in such a case, we can say that threads execute operations simultaneously, which is at the same time, literally. And we can, see another example when we still have multiple threads, but these threads actually do not execute anything in parallel. They execute operations in sequence, like one by one. And in such cases, we can say that threads are executing operations sequentially. So the interesting moment here is that why I'm showing you these two obvious examples. This is very obvious, full parallelism, no parallelism, yeah. The interesting thing here is that we usually tend to confuse sequential execution with synchronous execution. I heard it a lot of times and I continue to hear it everywhere. Actually, when people say threads are executing synchronously, when they are seeing such a picture like now. And to state their point, they say, for example, we have some semaphore which actually help us to synchronize thread executions. However, the interesting thing about such a case with a semaphore is that actually what we are doing, we are not trying to synchronize threads between each other. We are not trying to bind operations of one thread to operations of another. We are actually trying to serialize access to the resource. So if we, for example, kill the thread number 2, the thread number 1 will access resource and continue its execution because I don't care about thread number 2. Because all we do currently is we serializing the execution, not making it synchronous. And here comes the question. Okay, so if usage of semaphore to serialize access to the resource isn't synchronization, can we ever have a synchronization? Sure we can, But this has to be kind of a special case, for example, when threads are sending messages to each other, like in this example. So thread 1 sends a message to thread 2, and until this message is received, thread number 2 does nothing. And if thread 1 for some reason will be blocked, terminated, aborted, or something else, thread number 2 will never do anything. Because in such a case, thread number 1, its execution, and thread number 2, they're bound to each other. They cannot proceed without each other. There is no way for one thread to finish its work without having another to finish it. This is where we're saying that thread execution is synchronized. And serialization and synchronization is one of the first things ever confused by people when they are talking about parallelism. So let's get back to parallelism. It was, like a side note to explain why these things are bound to a circle of confusion. We will have more when we'll proceed. So in parallelism, we are focusing on a very interesting thing. We are trying to reduce the regions of sequential execution, so these wide blocks, and extend regions of simultaneous execution. This is all parallelism is about. Or if we can simplify it even more, we can say that it is focused on doing things at the same time. So that is what parallelism is about, doing something at the same time. So the next one in our list is multi-threading. And multi-threading actually is very interesting things because literally what it means anything what makes use of multiple operating system threads. I want to underline this, not our threads that we have defined at the beginning of the presentation, but operating system threads. And actually, we do not care how these threads are used. Everything that have multiple operating system threads is multi-threading. So for example, these threads can literally do nothing. And this is multi-threading, or a good example of multi-threading. Or we can have two OS threads which are executed on the same CPU, and actually they are executed as we saw sequentially, not in parallel. So they are not doing things at the same time. They are not doing synchronous on asynchronous calls. They are not synchronized. But this is still multi-threading. And the reason why I'm talking about multi-threading so much here is that because multi-threading is usually used in sense of parallelism, in absolutely the same way as serialization used as synchronous, in the same way multi-threading is usually used in sense of parallelism. So to see this, you can just imagine an example when someone says you, hey, this is a multi-threaded algorithm. Usually what they mean is an algorithm which makes use of multiple operating system threads to achieve parallelism in processing, or multi-threaded application. Absolutely the same. So it's an application which uses operating system threads to achieve parallelism in processing. So actually, this is the second major point of confusion in all this terminology, because we are tend to tie this multi-threading to parallelism, making it like an essential thing in it. While parallelism can be implemented without multi-threading, it's okay to implement it other ways. And the same happens with the serialization and synchronization. But if you're talking about multi-threading, it is important to remember that it is actually focused on using multiple operating system threads. And that's all. Every .NET application you have ever created is multi-threaded application, because when you start the application, you have GC thread, you have some threads in the thread pool, and so on. It's already multi-threading. You have to do nothing to make your application multi-threaded in .NET. And now it turns to concurrency. And this is the most subtle concept I ever met, because actually it is a model of a system which describes how this system manages multiple active threads. So this is really tough. I totally understand. So let's see some examples. So for example, if we use word concurrency in collections, actually what we are saying, and that there is a model in this collection that describes how this collection manages multiple threads which are access this collection at the same time without data loss or data corruption. We can apply word concurrency to JavaScript, for example, and concurrency in JavaScript actually describes how engine manages execution of multiple threads, including timer, request callbacks, and so on, to be active at the same time, while in the JavaScript they are not active at the same time, but still. And to better illustrate this, how concurrency can be important, and at the same it can be such subtle concept, is that we have a resource like this example, and we have two threads. In .NET, to make sure we can use this resource, we need a lock to make sure the access is serialized. So threads can access this resource one by one in order. However, if we imagine the same situation in JavaScript, while we set two timeouts with two functions, or we received 10 callbacks from backend, anything, we still do not need to do anything at all, because concurrency in JavaScript is pretty clear and straightforward. It is event loop, so everything is sequential by its nature. No locks required. So concurrency focuses on how system manage multiple active threads, and I want to underline that it's focused on behavior of this system. So not implementation. Concurrency doesn't care how we actually do this thing. It cares what behavior we state, to how the system would behave when there are multiple active threads. So we have discussed a lot about basic concepts, and I hope something of this was interesting to you and maybe even useful. But now let's focus on parallelism and actually on doing things at the same time. So parallelism is a multidimensional concept, and there is no single taxonomy which describes parallelism. However, because parallelism existed for a long time, there are few things that are well defined. So the first of these things is types of parallelism. So actually, types of parallelism focus on what is being parallelized using multiple threads. So by threads, again, I mean our threads, not operating system threads. So I'm still talking about dedicated stateful actors here. So the thing what can look strange, but actually it is the essence of types of parallelism. So for now, there are two mutually exclusive types of parallelism. It's a task parallelism and data parallelism. So task parallelism is all about parallel processing of tasks. And a task in this context is an action, or maybe a set of actions, which accomplish a certain goal using multiple threads. So we are parallelizing some task on multiple threads. And for example, of some real-life tasks, it could be calculating shortest path in the graph. We can calculate the distance between 2 points. We can save a record to the database. So in our case, we could grab all these 3 tasks and execute them in parallel, and we can say that this is task parallelism. So when you are hearing something about task parallelism, you for sure can say that they are trying to parallelize some actions or set of actions. The good way to think about task parallelism is to imagine a set of threads which actually do very simple routine, some receive task, process task, and return task result. That's all. Very simple routine. It can be really complex to accommodate some error handling, exceptions, and so on and so forth. But if you remove all this stuff, it is so simple, 3 actions. And on the other side, we can imagine a bunch of tasks. So using some scheduling mechanism or magic, we arrange this task and distribute them among threads to be executed in parallel. So while we are using such things like distribute between threads, like we have tasks of different size, if you paid attention to the bubbles, they have different size. So still task parallelism is not about how these tasks are actually distributed. It's also not about whether this task different complexity, whether threads have different processing power, and so on. All these things are implementation detail. They do not contribute to what task parallelism is. So always try to separate concepts from implementation detail. Task parallelism doesn't care about how we distribute it between threads. It only says we distribute tasks. and they are processed in parallel. So about data parallelism, it's very similar to task parallelism, except we are parallelizing data. So we are parallelizing processing of data using multiple threads. And there is no single definition of what data is. And for example, it can be a list of medical records, an array of solar images, a graph to process, anything, any data you can ever imagine. And from the visualization point of view, it's really simple. So we always have some array of data. Some. It really do not care what about its shape. It's just some data. And we have threads. So the peculiarity of data parallelism is that threads are usually executing absolutely the same algorithm. And this algorithm works on some part of this data. Then we somehow partition this data and distribute it between threads to be executed in parallel. So as with the same with task parallelism, data parallelism is not about how chunks are formed, whether these chunks are equal or not, whether threads are equal or not. No. Data parallelism is just about parallelizing processing of data and nothing more. So types of parallelism is a very high level concept. You actually can transform it literally into code if you want to. So this is very simple. I bet many of you have imagined how to implement them. But on conceptual level, they are talking about what is being parallelized and not paying attention to all other factors that we as developers meet every day. And here is where parallel programming models comes in. So parallel programming models fundamentally define how we achieve parallelism. So if types of parallelism say what we are parallelizing, parallel programming models are about how we achieve this parallelism. And while this may sound really, really abstract or really high level, actually it is very precise. And to understand this, I would ask you to imagine an Iis web server. Just imagine it, maybe an icon, and ask yourself how Iis achieves parallelism. Actually, unfortunately, I cannot see your answers. It would be really great to see how you answer this question, but unfortunately I can't through the online. And so I will provide my own answer. And this answer is very simple. Iis achieves parallelism by processing incoming requests in parallel. It is that simple. So there is no, some magic. Iis web server parallelizes all requests. That's all. And that is why it's a fundamental decision. If you change this, how Iis achieve parallelism, you will change the whole program. Everything will need to change. And currently, there are 4 well-defined parallel programming models. So let's go through each of it and see how they work. So the first one is independent parallelism. So imagine you have a few threads, and each of these threads receives some input and produces some output. The very important thing about these threads is that there is no dependencies between these threads. So the input we provide have no dependencies. And therefore, all these threads are executed in parallel or simultaneously. This is why it is, by the way, called independent parallelism. So these threads can execute absolutely any routine. So there is no thing about what these threads should execute. So this model can be used to exploit both task and data parallelism. And actually, most of the parallel programming models can be used for both purposes. But particularly this one is interesting because it is exactly how Iis achieves parallelism. Because Iis threads every request independently and process it independently. And even if this request somehow dark magic, it is still, you're making bad to yourself, not to Iis. And what is interesting, such a model can be applied not only on such application level like as we have described. It can also be applied to thread pool. If you think about thread pool, it also does the same things. It threads every request to thread pool as independent thing and executes them independently as much as possible. So the next one is pipeline parallelism. So imagine we have something to process and we have several stages. The first stage receives input, the initial input, and the final stage produces final output. In between, output of one stage becomes input to another one. So the parallelism is achieved on each stage. So the idea is that each stage is executed absolutely in parallel. So there can't be any dependency between stage 1 and stage 2. And each stage can have a different number of threads because they can have different time required to produce something, to do the actions they would like, and so on and so forth. So there can be different number of threads to maintain the pipeline throughput. But essentially, the idea is very simple. Each stage works in parallel. On each stage, we have different routines, because otherwise, if we would have the same routine on multiple stages, why do we have multiple stages? It looks very strange. So these different routines are executed by each thread in a stage. So all threads on the stage execute the same routine. And example, when you can see such a parallel model is any kind of data processing, like image conversion, video conversion. It also can be used in web crawlers. So web crawler picks up the URL, downloads data, parses it, and extracts data, and so on and so forth. So anything which require stage-by-stage processing. The next one is synchronous parallelism, which I mentioned in the beginning of the presentation. This one is kind of tough to get because it's very niche. So imagine we have some data. And also we have an algorithm which takes this data as an input and produces the new version of this data as output. Then this output becomes an input to the next iteration. So we are talking about iterative algorithms here. So the parallelism is actually achieved inside it. And it can be achieved quite clearly because one of the things that this schema guarantees us is that the data never changes its size. So it always has the same length. So what we do here is that we have multiple threads inside the algorithm which do processing in parallel. They always do the same amount of work because data size isn't changed. And they can do it as much as required. So it may look strange why we would ever want us to be bound inside of iteration. Is it will be better to process the data pieces by pieces, trying to parallelize everything? And actually, while it looks counterintuitive, the answer is no. If you cannot streamline the dependencies between chunks of data to make uninterruptible processing, then it might be much better to concentrate the processing within iteration to achieve maximum parallelism. And actually, this model is applied to many dynamic programming algorithms, to many iterative algorithms. So it is very natural on these algorithms because usually within the iteration, it is really rare when data have dependencies to each other. So when parts of the data are really closely related. So in reality, you can use almost independent parallelism inside this algorithm. However, it will still be bound inside the synchronous parallelism. And this example illustrates one interesting property of the parallel programming models and also types of parallelism is they can be nested to each other. So we can have synchronous parallelism, and inside it you can have independent parallelism, and one will be for data, one will be for task, and so on and so forth. You can nest them infinitely, as much as you want. So yeah, by the way, I forgot about this one. All threads are stopping their processing before next iteration starts. So no processing escapes iteration boundary. Okay, and next comes loosely synchronous parallelism. And what is interesting about loosely synchronous parallelism is that it is almost absolutely the same as synchronous parallelism, with small difference. The length of the iteration may vary because data size can change between iterations. So the natural examples of where you may encounter such processing it's any algorithm that has dynamic in time. So for example, you can imagine how you are calculating the area of water spill. So you spilled some water on a table, for example, and you can see that area is growing. So on each slice of time, you will have different amount of data to process, different area, you will have some object encountering the water, and so on and so forth. So this model is slightly loosened, so that's why it's called loosely synchronous parallelism, and saying that, yeah, the amount of data can vary between iterations. So we saw parallel programming models, and they really good. They can be mapped to a code almost directly. They are good at it. So if you spend a few minutes trying to think how you can implement all of them, it will be quite simple to imagine a C# code. However, as you might saw, there is really small talk about how data is distributed between threads, how tasks are distributed between threads, who starts what, who collides the results, and so on and so forth. So they are still kind of high level. You will still need to write a lot of things by yourself. And here is where parallel programming paradigms comes in. So they are much closer to the metal because they actually define how data in tasks are distributed and processed. And there are 5 well-defined parallel programming paradigms. And we will see through each of which right now. So the first one is primary secondary. Actually, it has a lot of names, and this is probably one of the most popular parallel programming paradigm you will ever see. I bet any of you, even all of you, have implemented it at least one time in your life if you have ever created more than one thread in your application. So here it is. Imagine we have a thread which we will call primary thread. And we have some request. So this might be data to process, or it may be a list of tasks to execute, something like that. Something that can be divided into pieces. Then our primary thread does some analysis and creates a bunch of secondary threads. Then it distributes the initial request between these threads. So actually it divides into subtasks and distributes them to secondary threads. These secondary threads do all the processing and return their results to the primary thread, which collates this result and returns the final output. So this is pretty simple. Anytime you create multiple threads in your main, this is a primary secondary parallel programming paradigm. You are doing it even without knowing it has a name. So let's see how it looks in code. So to do this, let's imagine an application. So we will imagine some interesting example during this presentation. So let's imagine an application which does the following. We have cars for sale or a trade-in, for example, and we need to analyze something about these cars. So we will analyze 2 things precisely. So one is analysis of windows for scratches, and the second is analysis of a car's body to see whether all functional elements are in place. So whether it has wheels, handles, and so on and so forth. So at first, here in our code, we accept some input and initialize an array to keep score values from a secondary threads. Then we actually create 2 threads. One thread will do the scratching analysis, and the second one will do functional elements analysis. So you do not see this in code because there is not enough space on the slide to write the actual processing. But for scratches analysis, we use images of windows. And for verifying elements, we use pictures of body. Then we start both of these threads and actually wait for them to be completed. And then when they are done, we are calculating the final score and return the result. However, the example I just showed you was using threads, and it is not really cool to use threads. We use tasks nowadays. So I removed the comments and created a new version of this algorithm using tasks. So as you can see, we use tasks here and no scores array because the return value, the score of each of the tasks, is stored inside the task. So we use a modern array task renol here, and it looks cool, much more modern. But I'm showing you this example not because I wanted to demonstrate how you can write code written in threads, how you can rewrite it in tasks. I'm showing you to ask you a question, and because we're doing this online, I'm asking you to think about the question. Do we have parallelism here? In both of these examples, is there any parallelism? So this kind of strange question. It's weird because we have parallel programming paradox in the title. We speak a lot about parallelism. We revised some concepts, we revised model types, and like in closer to the end of the presentation, I'm asking you a question whether we have parallelism here at all. It's strange, but it is one of the things I would like to underline to you. So both threads and tasks cannot guarantee your parallelism, because parallelism is not something you can express in code. You can express multi-threading in code. You can express synchronous and asynchronous execution in the code, but parallelism exists only in runtime. There is no way to express parallelism in code. You may express desire to make something in parallel, but you cannot express parallelism. You cannot have a guarantee that this will be executed in parallelism. So the reason is that if we'll use some microcontrollers or micro operating systems or something like that, there definitely will be the way to express parallelism. But when we are talking about high-level languages like C++, C#, and so on, and when we are talking about operating systems like Windows, Linux, macOS, I can say you for sure there is no way to guarantee parallelism. In 99% of cases, both of these examples will use parallelism. So these tasks and these threads will be actually executed in parallel. But if for some reason the operating system will be really busy, it for sure can say, I will schedule these both threads in one CPU and will switch them between each other in quantum of time, and you will have no parallelism. You will have pure sequential execution, even if you wrote a lot of tasks, threads, and so on. However, let's go further, because we still have time, but I would like to show more. And the next parallel programming paradigm is a single program, multiple data. So this is an interesting one. It starts from the data, and then threads. So the idea is very simple. We have threads which execute the same routine. This is important. Absolutely the same routine. And we have some data. This data is partitioned and distributed between these threads. Threads do the processing, return the result, and then this result is combined into final output. You might say, hey, this is exactly as the previous one. However, the most important thing is that all threads are executing the same routine, and this allows them to communicate, to resolve data dependencies, to send messages to each other, and lots of things which you cannot achieve in a primary secondary paradigm. There is no way, because it intentionally doesn't say anything about which routines they execute. So you cannot use single program multiple data for blind execution, but you can use primary secondary paradigm for this. And this paradigm is really hard to find an example in real life, because it's quite popular in algorithms like Gaussian elimination can be parallelized using this paradigm really, really good. A very high percentage of parallel execution. However, when it comes to general purpose application, it is hard to imagine an app which will require the same routine and message passing to each other. But I prepared one for you. So imagine we have an app which formats a book So we want to reformat a book to change styles, fonts, and so on. So what we have here? We are accepting input initializing our book object. Then we select each section and start processing of each section in parallel, using parallel invoke. So inside this routine, we at first format section content. So actually we change in font, styles, spacing, and so on and so forth. And this step is done absolutely in parallel between all the threads. However, next we need to update page information. So we need to update some references to previous pages. We need page numbers. We need to update some page numbers in our text. We need to update our internal information to reflect on which page we have which definition, and so on and so forth. And this cannot be done until we receive the information from previous sections. Because if you have ever formatted a Word document, you will understand what happens if you insert an extra space in the middle of the paragraph. The whole document just blows up and your tables are now split between several pages and so on and so forth. So here is exactly the same thing. So we have to wait. That is why we are blocking ourselves and waiting for sections to send this information to us. When we get the information, we update our information. So we change in references, definition, locations, and so on, and broadcast it down to other sections. So when the processing is completed, we are updating book information with the information of all sections. Like we are creating table of content, index, and so on and so forth. So this is how single program multiple data may look in code. However, I bet you won't find it in general purpose application because it's really hard to do such a processing. The next one is data pipelining. And it is fun because this paradigm is almost exact projection of pipeline parallelism programming model, with a small exception, or I would say specification. So when we are talking about data pipelining, the important thing here is that the input is usually treated as a stream of items to process. So we have some items, each items go through the pipeline, and we have stream of such items. And to illustrate it how it may look in code, I would like to say that in .NET, there is a separate library called Dataflow Library. It actually can be Googled like TPL Dataflow, which is built of things which help you to create data pipelines. So there is actually a lot of code, and they are called blocks here. So a lot of blocks which you can link to each other to create really complex pipelines. And the thing here is that they support anything from out of the box. So here's an example. This is the simplest web crawler ever. So it receives some links, downloads raw HTML, parses this HTML, and extracts the data. So in code, all of this beginning is an initialization of stages. The first stage download, the second parse, and you may pay attention that we are setting max degree of parallelism to 5. So we are saying we would have up to 5 threads working on this stage. And then we link all these things to each other. Then we push the data into pipeline, signal pipeline completion that we have no data, and then somewhere further we are processing the data from the pipeline. So the next paradigm is divide and conquer. And it is the hardest one to understand, and it is really hard to use properly. And it is about processing things in parallel from the single task to multiple small tasks. So imagine a task, and this task consists from two things, an algorithm and a data. What we are doing is that we split this task in a subtask with the same algorithm, but with a smaller portion of data. Then we are splitting them again in a much smaller tasks and the same algorithm, but with much smaller data. And only then we distribute these small tasks between threads. And threads process this task in parallel. Then we actually merge results of threads into bigger results until we achieve the final output using the same path as these tasks were divided. So this algorithm, this paradigm is naturally recursive. And let's see how it may look in code. And to demonstrate its usage, we will imagine an application which is processing huge images of space to look up stars. So at first, we are receiving some input and creating our really huge image. Then we are pushing our recursive processing, and when it is done, we are returning the report. So inside our procedure lookup stars, we actually do the following. At first, we check if image size is good to be processed. So if the image is too large, we partition the image into two images and start recursive processing of both of them. Then we use task when all to make sure we will be able to collate these results, in a single report. In cases when image size is of appropriate size, so you can imagine how we diving in one by one. So when we reach the image size that we are satisfied with, we simply process and return our part of the report. And then you can imagine that like we're splitting, and then collating things. So this paradigm is hard to get and hard to implement because it requires some good recursive thinking, and also it requires a really good knowledge of tools you have to make sure you are not introducing extra threads or extra processing. And the last parallel programming paradigm is speculative parallelism. So it is a very niche paradigm, and I'm almost sure never ever of you have used it. But there are cases where it can be really interesting and profitable to use. So we have 3 threads, and each of each thread has data. Now, imagine that there is a possibility, so this is important, a possibility of dependency between these data. So we do not know for sure. Starting from this moment, we have 3 scenarios. The first one is to thread these potential dependencies as strict dependencies, and therefore do not exploit any parallelism, just do sequential processing. But this is not good, because why then we need threads? We can, just process the data. The second way is that we can say, okay, let's assume there is no dependencies. Process everything in parallel and save a lot of time. But the real world is rough, and therefore, most probably we will see something like that. So we started processing in parallel, but some of the thread failed to process some of the data. Here comes the essence of speculative parallelism. So actually what we do is that we are saying, okay, we have detected integrity violation. Now we are executing the compensation action. We are executing the processing of compensated data. And actually what we have in the result, we saved some time. Yeah, it's not a pure parallelism, so no independent processing. We need to do some work, we need to spend some time for compensation, but we're still saving time. And what is interesting about this paradigm is that it is really, I never saw it myself. I would say like that. So I saw a lot of code, and I never saw speculative parallelism implemented ever. But it's fun to know it exists, and maybe some of you in your work will encounter a case and use it. If you do so, please share the results with me. I will be very grateful. But for our presentation, I prepared a synthetic example. So imagine we have employee profiles to process. So we use some system to process employee profiles. And each month, there are a lot of employees, new employees in our company. We are a very big company and a lot of new employees each month. So these employee profiles are matched against our database to make sure we have a proper references for father and son, husband and wife, and so on and so forth. So the problem here is that in most of the cases, these new profiles will not have dependencies to each other, because it's really hard to imagine that every month you have father and son joining your company. It's a rare case, but it still can be. So we would like to save our time, and we decide to use speculative parallelism here. So here it is. At first, we initialize profiles from some input, and we initialize a concurrent queue for profiles that we will need recovering. Then we execute processing of each profile in parallel. And if profile can be processed, we enqueue it in recovery queue. Then in the end, we are checking whether we have some profiles in recovery. So in such a code, we clear profiles, add range, clear recovery, and check profiles count. And if there are profiles to recover, we start processing of them again. So we do this in iteration and iteration. So the thing here is that this approach, in most of the cases, will be actually executed in the same efficiency as independent parallelism. So you would not have any problems. It will be maximum efficiency. In some cases where there are few errors, it will still be very efficient. However, if you imagine an error case at least for 50 in a multiple layers, like first layer of failure, second layer of failure, and so on, then this code will work slower than sequential one. So this is a trade-off of speculative parallelism. So today we talked a lot about parallelism. This was a lot of theory, and I hope it was interesting for you. But in the beginning of the presentation, if you remember, I mentioned that I asked you explicitly not to think about what stateful actor is. So what the definition of a thread. I will remind you that I defined the thread as a path of execution with an application carried out by a dedicated stateful actor. So the way I was trying to not specify who stateful actor is because all these models, paradigms, and so on, I demonstrated you today, will work if by stateful actor we will understand the obviously operating system thread. Or operating system process, we actually can write an application and start it multiple times. Or it can be a separate computer, or even a cluster of computers. So we can have a separate computer as a stateful actor, so we can have a bunch of computers. And everything I described to you today will still work and provide the same level of efficiency. And this will work even with humans. So this is the interesting thing because this stuff is universal. Imagine you are cooking a lot of dishes. You can use primary, secondary paradigm. You can less single program multiple data, like distributing potatoes between multiple cooks to make sure they cut it, and so on and so forth. So all of this stuff will still work. And this is really interesting. So these models are very universal. And at the end of my presentation, I would like to demonstrate you a small thing, how using all this theory, you can actually do crazy stuff. So I have switched to Visual Studio Code, and I really hope you can see it. So here's the thing I would like to show you. Let me scroll a bit. So what we have is a scheduler, our custom scheduler. And we are creating a few tasks. And this is a very bad design because we have tasks of tasks, which means that we have async wait inside our tasks. So this is probably a bad code. But let's focus on what we have. So we have two tasks, primary and secondary. And we start primary task using our scheduler. And in the end, we are waiting for both tasks to complete. So we are using nwrap here to make sure we are awaiting the inner task, not the outer one, because the outer one we will mark as completed as soon as we use async await. However, if we execute this code, you will see the following output. I have executed in advance to save some time. So the first thing printed is this line, so primary. The second line we see printed is this one. The third line is printed this one. And the last one is printed this one. So actually what you are seeing here is that when we started a primary thread, we executed this piece of code. Then we transferred the execution from primary thread to secondary thread, executed this line, switch it back, executed this one, then pushed the secondary thread to continue its execution independently, and printed this one. So actually what you see here is the cooperative multitasking. We have multiple tasks that cooperatively transfer control between each other. And you can implement this in .NET. In an environment where most of us rely on thread pool, we still can do crazy things. And we can do that because we understand that actually here, we have asynchronous execution because we are starting and then waiting. So we can ignore it and not wait. So this is asynchronous execution. However, both of these threads are executed sequentially, like we saw in the picture in the middle of the presentation. They're executing one by one, no parallelism here. And you can be sure because we have output like thread number 4 here. So it is executed by the same thread. So how it is implemented? It is implemented using our custom scheduler here for sure. So the implementation is not tricky, and I will try to explain it as fast as possible because I see we have really small time left. So actually our scheduler have a thread. This thread has an internal queue, and it extracts a task from the queue, checks whether this task has ever been executed by our scheduler. If not, we schedule it to our scheduler. If there is no continuation, we execute task. If there is continuation, we execute continuation. So this is quite simple. And also our scheduler implements such a switch control. So this is an internal class with all it does is a proxy access to our scheduler. So when we pause a task, we actually saving the continuation for this task in our internal dictionary. And when we are resuming the thread, we actually pushing it in the internal collection. So the internal collection is just a blocking collection of tasks here. So no magic. And inside our awaiters, so we have extension method which create our awaitables. And using the local thread local storage, they actually retrieving the instance of a switch control. So inside our awaitables, we return an awaiter, just passing the parameters down to it. And inside an awaiter, we are doing the following thing. We are saying, okay, this is not completed synchronously. We are forcing the machinery to create a continuation action for it. Then we are pause our task and resume the new one. And using this, we are implementing direct control transfer between two tasks. So for sure, this implementation can be made better. There are a lot of things that can be improved, but I think it is quite fun how you can apply the theory into practice. And this is all from me today. Thank you very much for listening. I hope I didn't cross the lines, and I still will have some time to answer your questions.
Cool. The whole presentation was so awesome that Konrad was rescheduled and Skulet's task was brought on board. And I think we could pick up like 1 or 2 questions. So let me start from the end. Preference TPL data flow over channels.
Okay, so channels are mostly for producing consumer stuff. So this is when you would like to have something produced and distributed and then received. TPL data flow is about constructing the pipeline. So this is the core difference. You actually can construct a pipeline with the channels, but TPL data flow includes built-in support for many blocks, built-in support for introducing concurrency on each block, and so on. So it is just simpler to use and less to write.
Awesome. I've got a request that there are some like really spicy questions in here and we should answer them all. We'll do our best. The next one related to Kitara software.
Actually, I didn't test this software, unfortunately, but I would like to, to write it down. Maybe later you can let me take a screenshot. Maybe it will work.
I mean, the comments are available in the chat later on.
I actually do not have experience with this software, so unfortunately I cannot answer anything regarding this.
Okay, another one.
Yeah, actually that is really true. So all the code we run always rely on some operating system. Even if it's really small, we still rely on it. So if we are taking a general piece of code like running on Linux or Windows, we have multiple layers. So first of all, to execute parallelism, we need at least 2 cores, at least 2. There can be parallelism on single core. There can be some sort of parallelism if we have multiple LU units, like in hyperthreading, but it is not a real parallelism. As we know, it's some parallelism on instruction level, really small. So to have real parallelism, we need at least 2 cores. So at first we depend on hardware. Then the next level is operating system. So most of the operating system provides functionality to bind an operating system thread to a core. So you have such a functionality in Windows. However, you do not have a way to dictate Windows which thread to execute on this core. So what you can say is that execute my thread on core 1 and this thread on core 2. However, operating system had a lot of application running on it. So if there is a need for other application, or what is really happening much more often, some network package came in and you need to do an interrupt, grab it and release it. So operating system can always stop your thread, do some work and resume it. Usually there is such thing as a quantum, which operating system use to make sure threads have more or less even time to execute. So this is a very complex mechanism. You can study Windows internals, for example, to understand how it works in Windows. It's really fascinating. So this is really, really interesting, amazing stuff. And it requires another lifetime to explain everything. And when it comes to .NET, it's another layer. So in .NET, when you create a thread, it's usually an operating system thread. However, it is important to remember that it depends on runtime implementation. So if Conrad implement a different runtime for this might be not operating system thread, but sure. So, but usually thread is operating system thread. So it applies the same rules as operating system thread. But when it comes to tasks, we usually tend to use a thread pool underneath. So it is rare when we define our own scheduler that I did in the end of the presentation. So usually it is a thread pool. And thread pool is an abstraction above the threads because it has internal queues, it has internal ways of managing load. So for example, it uses so-called high climbing algorithm. Yeah, so if you have a lot of requests, it will not create threads immediately. It will wait to see some saturation to make sure that you actually need more threads to do the work. So there will be a lot of moments on the high load, especially when your tasks will be actually executed sequentially. Or some will wait and some will execute. So I hope I was able to answer the question.
Yeah, and I hope that that you're part of the answer when you mentioned that it would take a lifetime to talk about this. That's just a topic for the very next one. So yeah, thank you for being with us. We are really running out of time, so we need to wrap up. Oleg, thank you for being with us, for providing all this knowledge, and yep, that was a perfect talk. So thank you again.
Very much.
Take care.
See you
Bye.
later. Bye.